Hey everybody. Today we're going to talk about number classes. That is, sets of numbers that define certain numbers in a certain way. Now this is an important idea because as we're exploring certain functions or formulas or theorems, we're often limiting to what types of numbers we're studying, or we're often seeking to see what types of numbers these things will apply to. And so we need to first have a clear understanding of how do we classify certain numbers in certain ways. This is actually something we've already started with, and which is really the first way of classifying numbers, and so that's what we're going to start with, and then we're going to continue from there. So what have we already started with? We've started with what we call the natural numbers. Now, as a reminder, we said the natural numbers are the same as the counting numbers. And so, just as we said 0 is not a natural number, we start counting with 1, 2, 3, 4, 5, and so on. That's what the natural numbers are. And we gave it a symbol as a way to define it. And we said it's like a capital N with a double bar. And in typing, you might use a bold capital N, but it's not really a way to do bold here without a lot of little squiggles and fill-ins. And I failed art, so we're not going to do that here. So anyway, capital N, and we say we define this to be equal to the set of numbers, and remember we use braces for sets, where I start with 1, and then 2, and then 3, and so on, and I use that ellipsis to show that it goes into infinity. And that's our first class of numbers, the natural numbers. These ones show up the most. We would probably spend the most time using them if I were to categorize this once I were to finish this YouTube channel and look at every single video I've done and what number classes we covered. We're probably going to use the naturals more than any other. But it's not the only one there, and sometimes we do need others, but it's a good starting point. Our next class of numbers is actually one we've already seen as well. It's what we would call a subset of the natural numbers, meaning we take some of the natural numbers and put them into a set in their own right. And these ones we call the prime numbers. And just like with the natural numbers, we're going to use a capital P, and we're going to double bar it, so like that, and we define this to be equal to a set of numbers. Now, I'm going to get real mathematically technical with you guys here. It doesn't have to be done this way, but I like to because it's kind of fun. How can we properly define the set of prime numbers? Well, remember, we said that prime numbers are all natural numbers that are only divisible by 1 and themselves, and it can't be a 1. So more accurately, it has exactly 2 factors. Well, we can sort of represent that here using mathematical symbols. So I started with this. I'm going to say that this is the set of all P that are elements of the naturals. Remember, that means is an element of, or belongs in the set of, or is from the set of. So P that is from the set of the naturals. Then we put a vertical bar and we read that as such that. So P that are natural numbers such that Q is less than or equal to P, and mathematically, we use this little caret to represent and Q divides P if and only if, oh yeah, IFF, that's a shorthand for if and only if, Q equals 1 or P. And that's right, we invert the caret for or, and then I close these braces. Do I expect you to memorize or even follow along with all of that? No, not necessarily, at least not in the future. But right now you can kind of see what I'm getting at with this. First of all, prime numbers are natural numbers. They're from the set of natural numbers. I define some variable Q that must be less than or equal to P, and it must also be true that Q divides P, meaning it factors nicely out of P, if and only if Q equals 1 or P. Q equals 1 or Q equals P. Those are the only ways that Q would divide P nicely. Then P is what we consider a prime number. Now it's a little silly. We would rather just kind of say, well, look, I'm familiar with prime numbers. Can't we just start it like we do the naturals, where we start to actually write the values out, like something like this? And that's fine too. And in fact, most of the time, that's how you're going to see the primes defined, is more like that. But this is the nerdy, mathematical, technical way to really begin to define the set of prime numbers. You will definitely not be needing this. We know what primes are. We've got that here. When we revisit primes in the future, that'll be all we'll really need to know. Let's go forward from here. Now, as mathematics evolved, we learned addition as a faster way to count things when you have more than one thing that you need to count together. And then subsequently we needed to be able to reverse that addition, what we now call subtraction, although that's really just adding the opposite. And sometimes when we would add the opposite or subtract, we would end up with nothing. I had 5 goats, and then I ate 5 goats. How many goats do I have left? I got 0 goats. So that 0 is not in my natural numbers, so we need to define a new set that would include 0. And that's actually pretty simple. I'm going to start with the set first, and that just looks like what you would expect it would. It's the set of numbers with 0, 1, 2, 3, and so on. It's almost exactly the set of natural numbers, but we've thrown a 0 in there too. This is something we call the whole numbers. Numbers that have no fractional part to them is really where that title came from. We obviously haven't even gotten into fractions yet, and that's fine. But they're so close to the natural numbers that they're not really worth giving their own special symbol for. It's not like we use a capital W and bar the middle lines or anything like that. So what you'll see most of the time is we're still going to use the same n from the natural numbers, but we're going to put a subscript 0 on it. And that just means it's the natural numbers with a 0. Now there's actually a few mathematicians out there which will actually consider this set to be the set of natural numbers. And so they're going to reverse define this n is going to actually represent this set. And so when they want to reference what are really the natural numbers without a 0, you might see them defining this set like this. The same capital N, but then they put a positive or a plus as a subscript to say I'm defining only the positive natural numbers, because 0 is neither positive nor negative. Well, I just want to make you aware of it. It's not what we're going to do here, and the majority of mathematicians don't agree with that anyway. What we're doing here, this n natural is without 0, and if we want a 0, then we'll subscript a 0 or whatever, or just say the natural's plus 0, or however else we want to do that. But that is the whole numbers. Let's keep going. Now, just as subtracting or adding the opposite led to this number that wasn't in the naturals, 0, I can go even further than that. I have 2 goats, but I owe you 5 goats. So I give you my 2 goats, but we're not even yet. Why not? Because I still owe you 3 goats. In other words, as soon as I start getting more goats in, the first 3 have to go straight to you. So how do I represent that 3 goats that I owe you? Well, that's where we use negative numbers. So I have negative 3 goats at that point. Well, obviously there are no negative numbers in my naturals or in my whole numbers, and so we have to define a new set. Well, it should be fairly obvious to see that every natural number can be represented with a negative number. 0 can't, because 0 is neither positive nor negative. It's the absence of anything. But I could take every one of my natural numbers and just put a negative sign in front of it as well. Oh, well, that's pretty easy then. So that's what I'll go ahead and do next. And again, I'm going to start by showing the set. So I think about it, if this goes into a positive infinity, then my negative numbers should be able to go into negative infinity. And so I think I actually start my set with a set of ellipses. And then I say I could come from negative 3, then negative 2, negative 1, then there's 0, and then there's positive 1, positive 2, positive 3, and again, those continue to go into infinity. So here I have both the positive and negative natural numbers and 0. And we think of these as, well, numbers. I mean, I think for the most part, if you were to ask to list out numbers, this would be basically the list we would probably come up with. And in German, the word for numbers is Zahlen, which starts with a Z, so we actually use a capital Z, doubling that middle bar there. And the word we actually use to define this set is integers. And we say these are the integers. They're the positive and negative natural numbers plus 0. And these integers actually form a very, very important set that we'll probably see a lot as well, almost as much as we'd see the natural numbers. But one thing I want to point out before we go on to our next set is notice how these sets fit nicely into each other. So far, the integers form our quote-unquote largest set, and that the whole numbers are contained entirely within the integers, as are the naturals, as are the primes. So all of these sets above are subsets of the integers. Now let's keep going. Now, as mathematics matured, we eventually discovered multiplication, which is just a faster way of adding the same thing over and over again. And of course, we needed to reverse multiplication, which is what we now call division, but that's really just multiplying by the reciprocal. And what we find is that when we multiply two integers, we always get an integer. Take any two numbers from this set right here and multiply them, you're going to end up back in this set. Actually, that's actually true for the naturals and the whole numbers as well. It's not true for the primes, by definition of the primes, but that's just a little side note. However, if I divide two integers, I'm not guaranteed to get an integer. By way of a quick example, take 3 divided by 2. I've got 3 pizzas. I'm going to share them with 2 people. How many pizzas does each person get? They get 1.5 pizzas, or 3 halves pizzas. And that number does not exist in my integers, so we have to define a new class of numbers. Well, when I divide two numbers, I'm going to get a fraction in some way, shape, or form. And a fraction is just a comparison of two quantities by division, which we can also call a ratio. So we say that division produces ratios or rational numbers. Now, in math, we also say the answer to a division problem is called the quotient. So we take that Q, we get a capital Q, and we double bar the left-hand side-ish, double curve it, I guess. And we say that we define the rational numbers to be fractions A over B. But we got to be a little more technical mathematically with this. It's not going to be as bad as it was with the primes. That was mostly for fun. Such that A and B are elements of or come from the set of integers, and B does not equal 0. Now, why did I place that restriction on B? Well, for the simple fact that it's impossible to divide by 0. That's something we call undefined. Now, before you get all smart with me and say, oh, isn't an answer just 0? No. The order of a division problem matters. Think about it. 3 divided by 2 versus 2 divided by 3 is going to give me 2 different answers. So 0 divided by 6 is not going to give me the same answer as 6 divided by 0. And 0 divided by 6 is 0. I have 0 pizzas that I'm going to share with 6 people. How many pizzas am I giving to each person? 0. It's just that simple. 6 divided by 0 says I start with 6 pizzas and give them to nobody, including me. How many pizzas does each person get? There's no answer to that question because those pizzas exist, but they're going nowhere. So it's undefined. Now, that's a very simplistic way of saying that. I've got a future video planned for why we can't divide by 0, but for the meantime, take my word for it, it's impossible. So that's just the one restriction. B can't be 0. But beyond that, A can be anything, including 0, and B can be anything else but 0 from that list. And I'm going to get some sort of fraction, and thus I have my rational numbers. Now, something else to notice here, too. If I let B equal 1, then I'm taking any value A and dividing by 1. Well, what happens when you divide by 1? Nothing. Everything stays the same. So if I take any integer from negative a billion to positive a billion and beyond, and I divide by 1, I stay the same. In other words, I'm still that same integer. So even though it's in the set of rational numbers, all of the integers are also in the set of rational numbers. So again, all I've really done is started from my initial set of natural numbers and just kind of expanded them, with the exception of the primes. The primes are kind of like the unique, let's just talk about them, but we're not going to really focus too much on them kind of set. They are important, though. But then whole numbers grew, and then the integers grew that, now the rationals grow it even more. So the rationals contain every number we've already found so far, and then it's all these fractions. We haven't spent a lot of time dealing with fractional numbers, but I'm sure you're aware of them. So the next thing is have we found them all? Are these all of the numbers? Well, it turns out even the ancients knew how to answer that question, and that's what we're going to do next. Okay, let's say I've got a square whose length of the sides are unit 1. And remember, units can be anything. This could be 1 inch, 1 foot, 1 meter, 1 mile, 1 whatever. And remember, we talked about squares. Squares have 4 right angles and all 4 sides measure the same. So here's my square with 1 unit on each side. Now I want to measure the diagonal of the square. And either diagonal is going to give me the same measurement, but that's the length I want to measure right there. How long is that length? How can we go about measuring that without a tape measure, mathematically knowing for sure its value? Well, I hope while I've been jabbering a little bit, it's come to you that we have divided this square into 2 right triangles. And we have already talked about how we can relate the side lengths of any right triangle through what's called now the Pythagorean theorem. So what I'm really doing is kind of ignoring this half of the square and recognizing that this is the hypotenuse of my right triangle. And we label the hypotenuse C. And these are my legs, A and B, which are 1 and 1. And we remember the Pythagorean theorem is C squared equals A squared plus B squared. So now we just substitute in and solve. Well, we said A is 1 and B is 1. Now square both of those. Well, what's 1 times itself? That's still just a 1. So I've got C squared equals 1 plus 1. And 1 plus 1, we're really doing hard math today. C squared equals 2. Now I want to know the value of C, so I undo the square, which is called a square root. So it's like taking the square root of both sides, and I have C equals, what is the square root of 2? All right, let's think about this. What number multiplied with itself equals 2? I have no idea. I guess I could kind of approximate it, maybe. Let's take a look here. Let's do this off to the side. I could say 1 is less than 2 is less than 4. That's a nice true statement. And I can take the square root, or more accurately, the positive square root of all three terms. Square root of 1. What times itself equals 1? Well, that's just 1. 1 times 1 is 1. So the square root of 1 is 1. And square root of 4, what times itself is 4? Well, 2 times 2 is 4. So 2 times itself, so square root of 4 is 2. So that means the square root of 2 is somewhere between 1 and 2. Where? I don't know. And since I don't know the answer, I kind of leave it where I am. I actually have this, as of right now, is my answer. C is the square root of 2. That means this length of a diagonal of a unit square is just the square root of 2. Well, that seems very abstract, not very helpful, and it's not. And here, don't pull out your calculator. I'm not asking you to do that. The calculator knows a little bit more than we've learned so far. But what we're going to do is we're going to try to figure out the value for the square root of 2 by exploring what kind of rational number it could be. Okay, to learn something about the square root of 2, what we have to do is start with something that we assume is true about it. We don't know anything about it right now, so we might as well go with what we know. And I'm going to assume it's rational. And that's how we write it. Assume the square root of 2 is an element of the rational numbers, or just assume it can be written as a fraction. So let's explore what that leads to and see what we can learn about the square root of 2. Well, the next step is to say, well, what does it mean to be a rational number? Well, it means that I can say this fact right here. The square root of 2 must equal a over b. And remember, there's a restriction on a and b, where a and b are both elements of the integers, and more importantly, b can't be equal to 0. Okay? So I know a and b are integer numbers, and b is not 0. Well, what else do we know about fractions? Well, again, thinking back to elementary school, hopefully you remember reducing fractions. Fractions aren't always in a fully reduced form. For example, 2/4. I have 2 out of 4 things. That's great. That's no different than saying 1 out of 2 things. It's the same as 1/2. And 1/2 is fully reduced. I can't find any more common factors between the numerator and the denominator. So it's safe to say that no matter what values I find for a and b, I could always fully reduce them down to some fraction that can't be reduced any further. So I might as well just go with that and say, you know what? Let's just assume a and b are already fully reduced. Well, that's going to mean 2 things. One, it means they're both going to be positive. Why? Well, if they were both negative, we know, first of all, we know the square root of 2 is positive, and so these are either both positive or both negative. If they're both negative, then I can say, well, they have a -1 in common, and I can cancel that out and bring them down to both positive. And 2, it means that their greatest common factor equals 1. So what does that mean? It means if I look at all the numbers that multiply nicely into a or into b, then the only one they have in common is the number 1, which doesn't change anything. So we write it like this. we say let the GCF of A and B equal 1. That's just mathematical terminology for greatest common factor, which means this fraction is fully reduced. And then we know that A and B are greater than 0, meaning A and B are positive. Okay, that's just a consequence of all of this. We don't lose anything by understanding that fact, but it makes us more thorough, which is what math is really all about. All right, here's what we have. This is the math we have to work with. Square root of 2 equals A over B. Let's explore that a little bit. Let's start with this. I'm going to multiply both sides by B. All right, well, this is going to give me the square root of 2 times B equals A. And I don't like working with that square root of 2, but I can undo a square root by squaring everything. So I can square both sides of this. And that means my square goes to each factor inside these parentheses here. The square root of 2 squared, well, that just cancels everything out, and I'm just left with 2. And then I have B squared equals A squared. All right, well, what does that tell us? It tells me that A squared is a multiple of 2. And if you're a multiple of 2, you're what we call an even number. So what do we know about even numbers? Well, we know one thing, they're multiples of 2. We also know another thing, they're essentially half of the positive numbers, or the natural numbers in this case, which is what A and B are based on these restrictions here. So half of them are even, and the other half are odd. So we can think about dividing the natural numbers into two disjoint sets, meaning they have no overlapping values, all of the evens and all of the odds. So what can I learn from that, from even numbers and squaring numbers? Well, let's take a look over here off to the side. If I have an even number, then it's a multiple of 2. So that means I can write any even number in the form 2 times n. Okay? So again, n is going to have to be a natural number, but it's a multiple of 2. So let's say I had the number 8. Then n is 4. 2 times 4 is 8. Now what happens if I square an even number? All right, so I square this even number, then my square goes and distributes inside, and 2 squared is the same as 2 times 2, and I'm just going to write it out as that, 2 times 2, and then the square goes into the n, and then it's times n squared. And I can kind of group this in a way that might make a little more sense. I can separate everything but that first 2. And what does that tell me? Well, it tells me that I square an even number and I get a multiple of 2. That means I get another even number. So an even number squared is an even number. Now that doesn't tell me anything about the reverse. It doesn't tell me that if I square root it I'm going to get an even number, but that's okay. I'm getting somewhere. All right, so an even number squared is an even number, has to be. What about an odd number? Well, how can we define an odd number? Well, we can start with the fact that an odd number is not an even number, so it can't be a multiple of 2. Well, counting by 2s, that means I'm offset by 1 from those multiples of 2 to be an odd number. So we represent odd numbers by starting with an even number and then just add 1 to it. So this can be any odd number. So if I think about the number 9, then I can think n would equal 4 in this case, because it's 2 times 4 and then plus 1, which would be 9. And then I say, what happens if I square an odd number? Well now we've got a binomial squared. And so we have to remember, how did we go about doing this? Well, we did this through distribution. So let's write that out. It's 2n plus 1 times itself. And then we have to distribute every term from the first binomial with every term in the second binomial and add them all up. So we start with this. It's 2n times 2n. All right, well that's going to give me 2 times 2 times n, which is n squared, plus, and then I've got 2n times 1, so that's just 2n, plus 1 times 2n, that's just 2n, plus 1 times 1, and that's just 1. Now we could at this point combine like terms, try to simplify, but that would just be more work for what we're trying to prove. what I recognize here is that in my first three terms, I have a common factor of 2, which I can factor out front a set of parentheses, but only from the first three terms. So by doing that, I'm factoring out this 2, and what's left inside, here I took this 2 out, so I'm left with 2n squared, plus, here I took this 2 out, I'm left with n, plus, here I took this 2 out, so I'm left with n, and that's what I took the 2 out of, so I closed the parentheses, but I still have my leftovers here, plus 1. Now what does that show us? It shows me right here, this is just some natural number, because it's just natural number times natural numbers in here, and then multiplied by 2, which means this first part is even, and then add 1 to it. And that 1 offsets it from the even to make it odd. So we started with an odd number, we squared it, and we got an odd number. And so just like with the even example, even number squared even number, we know that squaring an odd number must give us an odd number. Well, if I've squared a number to get another number, then I know it's a perfect square, so I can take its square root to get a nice integer value. And what I find is that if all even squared give me even and all odd squared give me odd, I've covered everything, which allows me to now say the reverse must be true. Given that they're perfect squares, the square root of an even number must be even, and the square root of an odd number must be odd. So we take all that, come back here. If a squared is even, then the square root of a squared, or a, must also be even. So a itself is an even number. So I say, all right, let's define a as an even number. Let a equal, let's call it 2c, where c is some integer. So we can be a little more specific there, where c is an element of the integers. And let me kind of separate us out here so we don't get too confused. And now I can substitute that in for a. All right, so I left off right here, so I have 2b squared equals, instead of a, I'm going to write 2c and then square it. No big deal. All right, distribute that squared, and I have 2b squared equals 2 squared is 2 times itself, that's 4, and then c squared. And now I'm going to go ahead and divide both sides by 2 to isolate b squared. If I divide by 2 here, I'm left with b squared. Divide by 2 here, so 4 divided by 2, that's 2c squared. And hopefully you see a pattern. I said that a squared equals 2b squared means that a squared is even. So b squared equals 2c squared means that b squared is even. Oh, excellent. So if b squared is even, what we found here means that b must be even. So I go ahead and write that out. Let b equal 2d, where d is some integer. So d is an element of the integers. And substitute that in. So I've got 2d, the whole thing squared, equals 2c squared. Distribute that exponent. 2 squared is 4. D squared equals 2c squared. And now here what I'm going to do is I'm going to go ahead and divide both sides by 2, and then also divide both sides by d squared. So I get numbers on the left and variables on the right. So I've got then 2 equals c squared over d squared. We're actually done. But what have we just found? We have to be careful and think about everything that we just found. Going back to the beginning, we said that the square root of 2 equals a over b, and that it is safe to say a and b are in fully reduced form, because there is a way to find that. Once I found some fraction a over b, if it's not already fully reduced, it's possible to fully reduce. But then I said a could really be thought of as 2c, and b could really be thought of as 2d. Well, now I have a common factor of 2 in for both of those. which means I can reduce it further. So this wasn't in fully reduced form. No, wait a second. Then maybe it's just as simple as, well, A and B were never in fully reduced form. But think about it this way. The math has no way of knowing whether or not A and B are fully reduced form. In other words, what the math says is that no matter what I find for A and B, I can always reduce it further. But that's not possible. There's going to have to be a spot where it ends, which means we found what's called a contradiction. In Latin, we say reductio ad absurdum, meaning a reduction to an absurdity. That is a proof by contradiction. Doing math where I've made no mistakes, I come to a contradiction, something that's absurd. It does not make sense. I've basically said it's always reducible. There will never be a time when it's fully reducible, which is not possible. So if all the math is correct, there's only one thing that can be wrong: my initial assumption. Because all of this was based on this being true. So what does that mean? It's actually square root of 2 is not a rational number. That's what all of this proved to show, which means we've just found a new class of numbers. And if it's not rational, we call it irrational. Before we continue, for simplicity, I left off the limitations we place on rational numbers, meaning A and B are integers and B does not equal 0. We can go ahead and assume we're going to be comfortable with that from here on out. This is just to save space. Now we've just discovered there are numbers that are measurable, like the diagonal of a square, that are not rational, and we call them irrational numbers. Now, in and of themselves, the set of irrational numbers is not a set worth studying. It turns out that they can fit into multiple types of subclasses of their own, most of which have no important properties that we really care a whole heck of a lot about. It's really more like they're numbers that just aren't rational. That's really what it is. So we don't have a way to define them. So more importantly, we now need to define a larger set of numbers that includes both rational and irrational numbers. And before we can do that, the name that we use, we need a little history for that. So first we're going to start with a little kind of motivation. First of all, you should probably remember from school something called a number line, which was usually probably straighter than the one I just drew. And in the middle of the number line, we've got a tick mark, and we call it 0. And there's usually a bunch of tick marks on here going both left and right. And they're labeled with the integers. So here's -1. I don't know why I put two negatives there. Here's -2, here's -3, here's 1, 2, 3. And we think about this line representing a continuum of numbers, meaning there's no smallest number, no gap in there in anywhere. The tick marks represent my integers, and anywhere in between represents these other numbers. And we know that rational numbers exist. For example, when I said 3/2, 3 halves, we know that's going to be right around there. That's going to be 3 halves. We even talked about reversing that, 2/3 or 2/3. And we know 2/3 is going to be right around here. We can also talk about the square root of 2. Now, we're not going to exactly calculate what its value is, but what we can talk about is where it is approximately. And you could use a calculator for this, and we get it's around 1.4-ish, and so we'd find maybe somewhere around here would be the square root of 2, but we can definitely order these numbers. Given any number on this line and any other number on this line, I can tell you which one's bigger than the other. And we can go in between them as much as we want to try to find an order to all of them. This is our number line, and this is what we say. These are our numbers. These are all the possible numbers that could exist, right? And so if it's not in this list and it's on this line, then it must be irrational. So that's kind of where that comes from. And if I put this list together with those irrational numbers, those numbers on this line that aren't in this list, then I get this line, which seems kind of like it's recursive on itself. So I'm defining this line based on numbers that are partly on this line, that are in this own set, and then all the other numbers that aren't in this set. And that's actually part of the trouble we run into, or I should say ran into, mathematically, trying to define this list of numbers. And we run into some other trouble too, which we're going to cover in a little bit. But before we do that, we're going to talk a little bit more about how we can kind of identify irrational numbers. Now, most of you out there probably don't have a calculator with a computer algebra system, which means if you plug in a division problem that doesn't give you a nice integer, you're going to see not a fraction, but a decimal. Just like when you plug in the square root of 2, or even if you plug in e, you're going to get a decimal. And so what we need to do is we need to understand how do decimals work, and to do that, we need to understand the idea of place value, and to even understand that, we need to set a base number for our number system. So in the world, pretty much universally, we used base 10. What does that mean? It means we're going to use 10 digits to represent all possible numbers. How do we come to that conclusion? Because we have 10 fingers and thumbs. That's literally the reason why. It's so easy for us mentally to group things in tens because we can see them on our fingers that we've just stuck with that. There's no reason it has to be 10. An alien race, maybe with only 2 fingers and a thumb on each hand, might use base 6. But all of the math they would develop would be the exact same. They would just have a different base number system. So that's no big deal. But that's what we use, and so that's what we're going to stick with here. So, for place value, what you have to imagine is like a series of infinite boxes, just in a row that just keep going and going and going, much like the Energizer Bunny, for those of you who are old enough to remember that. And at some point, I'll put these ellipses here, these things get separated by what we call a decimal point. Decimal, from the Greek or Latin, I don't remember which, base 10 is what that means. That's why it's a decimal point. If we use a different base, we'd call it a different name. And that decimal separates me in my exponents. I'm in base 10, so to the left, I start with 10, and I raise it to the power of 0. And then as I go one more place to the left, I have 10, and I raise it to the power 1. And then one more place to the left, I have 10, and I raise it to the power 2. One more place to the left, I have 10, and I raise it to the power of 3. And I keep going into infinity. The next one is 10 to the 4, 10 to the 5, 10 to the 6. And likewise, I go to the right. So to the right of the decimal point, well, look at the pattern. 3, 2, 1, 0. What comes next? That's just a negative 1. And then to the right again, I've got 10 to the negative 2. And to the right again, I've got 10 to the negative 3. And keep going into infinity. 10 to the negative 4, 10 to the negative 5. Okay? These are the representations of the place values. You probably know them better by their worked out values, which you would have learned in elementary school. Well, what is 10 to the power of 0? Well, anything to the power of 0 is just 1, so this is the ones place. And what's 10 to the power of 1? Well, that's just stays the same, it's 10. So this is the tens place. And this is 10 to the power of 2. What's 10 times 10? That's 100. This is the hundreds place. And likewise, 10 to the power of 3 is the thousands place. And you know how we keep going from there. That's where we get those names from. Now here may seem a little more complicated, but don't fret. Remember, a negative exponent means I just take that power and move it to the other side of the fraction. So this is going to move into the denominator. So this is really 1 over 10 to the 1. And 10 to the 1 is just 10. So this is really 1 over 10. Or 1/10, or the tenths place. And this is really 1 over 10 squared, and 10 squared is 100, so it's really 1 over 100, or the hundredths place. And likewise, 1 over 10 cubed, which is 1 over 1,000, or the 1,000ths place, or thousandths place. And that's where that naming convention comes from. And then I'm just filling in the blanks with numbers. So if I were to, on my calculator, again, do 3 divided by 2, the answer on the calculator is 1.5, which means there's a 1 right here and a 5 here. And what about the rest of the boxes? Well, we just think of them as being strings of infinite zeros, but we just don't write them. It's a little weird to think like that, but it actually turns out it's kind of important. So we're going to go ahead and leave that thought process there. So if the boxes are blank, we think of them as zeros into infinity in both directions, but we don't actually write them down. All right? So why did this work? Why did 3 divided by 2, or 3 halves, give me 1.5? Well, these boxes tell me how many of these place values we have. So this is saying I have 1, 1, and 5/10. So I have 1 times 1 plus 5 times 1/10. That's what that tells me. And so this is just 1 plus 5/10, and 5/10 reduces to 1/2. This is just 1.5. Well, 3/2, we said 3 divided by 2. 3 pizzas given to 2 people. Each person gets 1.5 pizzas. That makes sense. So 3/2 and 1.5 are the same. And so as a decimal, we would write it like that, because a 5 out of 10 is the same as 1/2. That's why we put a 5 there. And that's how place value and decimals work. So what kinds of decimals can we get here? This is the simplest kind. It's what we call a terminating decimal. In other words, ignoring the zeros in front and at the end, it means that I'm done. It is a finite number of digits that I write here. You probably also remember, even from elementary school, that that's not always going to be the case. When you're doing your long division and you're subtracting and you get a 0, you know you're done. That's a terminating decimal. Sometimes when you're doing that subtraction, you get a remainder that you've had before, which means you're going to start a repeating pattern. And it's a pattern that will repeat infinitely. For example, I could have even nothing in front of the decimal point, so I have nothing here, and I might have a 3, a 3, a 3, a 3, a 3, a 3, and that goes on and on forever, a repeating 3. But I got that from a division problem. Which division problem? We'll explore that in a bit. But I could repeat those digits for forever, and it's still a decimal, and it came from a division problem, which means it's still a fraction. So I do my long division, I get a remainder of 0, that's a terminating decimal. Well, that's long division. That's a rational number. So a rational number can give me a terminating decimal. I do my long division, I get a remainder that I've had before. I start a pattern that's going to go on into infinity. That's a repeating decimal, an infinite repeating decimal, but it came from a fraction. It came from a rational number, a division problem. And so repeating decimals are also rational. So I can turn a fraction into a terminating decimal, or I can turn a fraction into a repeating decimal. What about vice versa? Let's look at that one next. This time, let's start with a decimal and see if we can turn it back into a rational representation. So again, we'll go back to the whole 1.5. We know where this comes from, but how can I start with this to get to where it came from? Well, it's actually very simple. Take a look at the very last place value for my digit. This is a terminating decimal. This is in the tenths place, or 1/10. What I do is I take this entire number as if there's no decimal point, and I multiply it by that very last place value. So in this case, it's like saying 15 times 1/10, and that's the same as 15 over 10, and then I reduce. What common factor do I have between 15 and 10? I can divide both sides by 5. So if I divide by 5 here, divide by 5 there, I get 3 over 2. And I turned my terminating decimal back into a division problem, basically, a rational number. And that works for any terminating decimal. I can even do something like this, 25.125. All right, my last place is the thousandths place. So I write this number as if there's no decimal, 25,125 times my place value, 1,000th, which is no different than 25,125 all over 1,000. And that's actually an answer right there. I don't have to fully reduce, but I can. But it's the idea that there is a rational number right there. It's just not in fully reduced form. And so I'm not even going to worry about it because that's not the lesson for this one. You can do that on your own. But what if we've got a repeating decimal? So we see now with a terminating decimal, it's easy enough to turn back into a rational number. So we can say all terminating decimals are rational numbers. Let's talk about all repeating decimals. Let's let x equal this repeating decimal right here. So a whole bunch of 3's repeating. Okay? Well, what can I do with that? Let's multiply it by 10. All right? So if I were to multiply the left side by 10, I get 10x. And if I multiply the right side by 10, all that really does is move the decimal one place to the right. So this is the same as 3.33333 on into infinity. Because there's an infinite number of 3's, and so there's still an infinite number of 3's. I've just got one place to the left of the decimal point now. And now I can actually subtract these two things. So I can subtract the left side. I've got 10 x's and I take away 1 x. Well, I'm left with 9 x's. And then on the right side, well, what happens with these 3's, and these 3's, and these 3's, and these 3's? These are being subtracted from each other. 3 minus 3 minus 3 minus 3 minus 3, those are all zeros. So these things all cancel out, and I'm left with this. 3 minus, well, nothing, so I have 0, which means I'm left with 3. So now I've created this problem right here. 9x equals 3. That's very easy to solve. Divide both sides by 9, and I get x equals 3/9, which, as a fraction, reduces very, very nicely to 1/3. And what I found is that, remember, x equals 0.3333 and x equals 1/3, therefore they're the same thing. And so 1/3 is this repeating decimal. Now that worked out nicely for this nice simple one. I turned a repeating decimal into a fraction, but it turns out I can do that with any repeating decimal. Let me show you how. Let's consider this more complicated one. X equals 0.142857, and then I'm going to draw this bar over top of it. You might remember that from school. That bar means take those digits and repeat them into infinity. So this is 0.142857, 142857, 142857 over and over and over and over again infinitely. Now here we had one digit being repeated, the 3, and here we've got 6 digits being repeated. So here I multiplied by 10, or we can think of it as 10 to the power of 1. So here I'm going to multiply by 6 digits, so it's 10 to the power of 6 is what I'm going to actually do. By doing that, I'm moving the decimal 6 places, and so this becomes 142857.142857 repeating into infinity. This is a million, by the way. So it's a million x, and then I can do the exact same thing as I did before, and I can subtract them. So I've got a million x's, and I take away 1 x. So I'm left with 999,999 x's equals, and again, lining up my decimals, all the decimals cancel, and all I'm left with is this part here, which is 142,857. And then I solve for x by dividing both sides by 999,999, and I get x equals 142,857 999,999ths. And then I check to see if I can reduce it. Now I don't have to do that, but I can. But in the meantime, I stop and say, this is a rational number. And I started with a repeating decimal, and so I've turned this repeating decimal into this rational number. And just for fun, check me, make sure that I'm right. This should reduce all the way down to 1/7, by the way. And so it's the idea that I could do this with given any sort of repeating decimal. I can get it to the point where I can multiply by enough powers of 10 that ultimately I would have all the repeating stuff lined up that I could subtract them, and then I would just be ended up with a problem like this, and I could divide by what's left over, and then whether or not I want to, I can reduce, but either way I found a rational number. So all rational numbers can be divided out to find either a terminating decimal or a repeating decimal, and all terminating decimals can be shown to be rational, and all repeating decimals can be shown to be rational. So what does that leave? That leaves only one other way, using decimals, to write out numbers that are on our number line. They can't be finite, because if they were finite, like this, a terminating decimal, well, then I would have a rational number. So irrational numbers can't be finite, so they have to have an infinite number of decimals. And they can't ever repeat, because as soon as I get some sort of repetition like this or like this, I can turn it into a rational number. So another way to think about irrational numbers are decimal numbers that go into infinity but never ever repeat. So we can say that about the square root of 2. The square root of 2 is some decimal number that goes into infinity and there's no repetition ever, but it still fits on our number line. Now we need to get into how do we classify those numbers on our number line. Now, just as when mathematics evolved and we found some inverse operations, we ultimately found new numbers that we had to classify. That's how we're going to keep going from here. So we started with natural numbers, we come up with addition, and then we invert it with subtraction, and now we need to add on to our numbers, so we have integers. Then we come up with multiplication, we have to invert it with division, we come up with some new numbers, these rational numbers. Well, what's the next step? Well, the next step is exponents, when I do repeated multiplication. Well, given any number on this number line, raise it to any power, and you're going to get a number that's on this number line. That's awesome. Now, invert exponents. Well, that gets a little more complicated, so we're going to actually keep it really simple. We're going to only invert one exponent, the square. So think about x squared, and then I think about undoing that, and that's where we have square root. That's how I invert the square. Now let's think about what happens when I square a number. All right, I'm going to divide this number line into 3 sections. I'm going to divide it into the negatives. I'm going to divide it into 0 and the positives. So I'm going to have 3 disjoint sets on my number line. Remember, disjoint means they have nothing in common. All the negatives, just 0, and all the positives. All right, I'm going to start from the right-hand side. What happens if I take a positive number and square it? Well, remember, it's multiplying with itself. So I'm having a positive times a positive. That means I get a positive. All right, so I can kind of think of it this way. I'm going to abbreviate here. Positive squared equals positive. Okay? Now think about 0. What happens when I square 0? Well, 0 is neither positive nor negative, but what's 0 times 0? That's just 0, right? So I've got 0 squared equals 0. Okay. And now, negative numbers. Take any negative number and square it. Remember, you're multiplying with itself. So like negative 3 squared is negative 3 times negative 3. It's a negative times a negative. Well, what's a negative times a negative? Well, that's positive. And that's every number on my number line. So when I square any number on my number line, I either get positive or I get 0. In other words, I'm saying x squared has to be greater than or equal to 0. So if I'm going to undo a square, well, if x squared is greater than or equal to 0, then what I'm undoing in here has to be greater than or equal to 0. I'm not allowed to put a negative number in there. But why? What would keep me from doing that? What would keep me from asking this question? What's the square root of negative 2? It turns out the only thing keeping me from asking this question is this recognition right here. I can't square a number to get a negative number, therefore I can't talk about square rooting a negative number. And so we just said it's not possible. For hundreds of years we treated this like division by 0. It's not possible, it's undefined. But then we ran into a little problem in the 15th or 16th century when we were trying to solve what's called a cubic polynomial. We don't have to know what that is right now, we'll deal with that at a later video. But essentially, the only way to come up with a solution when we knew there were solutions was to, at some point, have to deal with something like this. Maybe it wasn't negative 2, but it was negative something. We had to deal with it. And so, after we dealt with it, it was gone. There were no more square roots of negative numbers. Everything worked out fine. Everything sat nicely on this number line, but we still had to deal with it. And so, we came up with this idea of like a placeholder. Let's just pretend there's something there for now, and then we won't worry about it if it doesn't go away. We'll just kind of ignore it and just say, well, that doesn't make any sense, much like division by 0, which, by the way, there will never be a solution to division by 0. Turns out we do have a solution here, and the solution is what we did as a temporary placeholder. We said, well, this can't be real, so it must be imaginary. So let's talk about the imaginary unit. Let's call it I. And we define this as to say, if I square this imaginary unit I get the answer negative 1. There is some fake number out there that I can square to get negative 1, which means if I take the square root of both sides, then I get I must equal the square root of negative 1. Now, technically, we could say, is that the positive or the negative square root? But once we've studied these numbers more, that actually turns out to not have meaning. And whichever one you pick, as long as you're consistent, you get the same answers. So just for simplicity, we leave off any positive or negatives in front of the square root, and we just say I is the square root of -1. So we create this imaginary value. Well, if this one's imaginary, what does that say about all of these numbers here? Well, that means they're real. That's what we call them. This whole long thing was to get to why we got the name for these numbers. We call them the real numbers. Okay, so now we have a name for all of our numbers on the number line. We call them the real numbers, and now we need to find a definition for them. We're going to get a little complicated here with this, but trust me, it'll make sense. Let's start first with the symbols. It's the real numbers. So we use a capital R, and we double bar the left line, and we say that we define them to be, well, there's one way to define them. It's the set of all rational and irrational numbers, but that doesn't work because remember we define irrational numbers to be any real number that's not rational, so that doesn't help. But then we go back to the decimalization and we say, how did we define irrational numbers based on decimals? And we said, well, decimals can be in one of three states. They can terminate, they can repeat infinitely, or they can be infinite but have no repetitions. And that's really everything. And we even said that with terminating decimals, you could still think of them as an infinite decimal if you think about an infinite number of zeros, both to the right and to the left. And so that's the clue that we're going to use to basically define this. So it's going to look a little complicated, but I hope it makes enough sense. So again, I'm thinking about coming from infinity, and I'm adding, let's say, 10 to the power of 2 times d sub 2 plus 10 to the power of 1 times d sub 1 plus 10 to the power of 0 times d sub 0 plus 10 to the power of -1 times d sub -1 plus on and on and on and on into infinity. Okay? Hopefully that looks familiar. These are my place values. This is my hundredths place, my tenths place, my hundreds place, my tens place, my ones place, my tenths place, and so on that way and so on this way. And they're all being multiplied by some digit. Well, what are our digit choices? And we say this means that the d sub i's, where this is just any of those d's, are elements of a particular set of numbers. In this case, it's 0, 1, all the way up to 9. I think that went off camera there a little bit, didn't it? All right, here we go. Can you see that now? There we go. So anyway, that's really ugly, that's really complicated, but it's the best real number definition we have using the kind of algebra that we know. It basically says that consider an infinite number of place values where each place value is denoted by a successive power of 10, and multiply each of those place values by some digit from this set, 0 through 9. So there could be an infinite number of zeros in either direction, but that works. And we say those are the real numbers. Now even this is kind of a weak definition, believe it or not. There's a couple of modern algebra reasons, or group theoretic, or even field theoretic reasons for that. Stuff that even goes a little bit above beyond what I can do. And so we're not going to get into that. So for our purposes, this is an acceptable definition. But here's where I want you to take away from this. Real numbers are anything you can fit on the number line. If you can fit it on the number line, that's a real number. So what about imaginary numbers? Do we actually pay them any mind? Do they get to fit into a class of numbers all by themselves? Or what do we do with them? That's what we're going to see next. All right, here we've got our number line again, or now, more accurately, our real number line. And we've talked about this idea of an imaginary unit, where we basically defined this quantity I to be equal to the square root of -1. And we know it cannot exist anywhere here on this real number line because it's not a real number, because the square root of any real number must come back to being real in order for it to be on this line. So we say that it's got to be somewhere not on this line, but if it's still a number, and if it's still one we want to consider, it has to be somehow connected to this line. And in mathematics, when things are connected but independent, we often say that they're orthogonal. Graphically, it means they're perpendicular. And so what we actually picture is another axis here. And I'm going to intersect it right here through 0. So I think about an axis that's vertical that intersects my real axis, and this is what we call the imaginary axis, or I. And again, we're going to treat up like positive, so we would call this positive I, this would, or just I guess, this would be 2I, and this would be 3I, and this would be minus I, you don't really want to say negative, and this would be minus 2I, and this would be minus 3I. And so what we want to recognize here is that we don't just have two lines intersecting each other, but we have their plane that they create. Remember, a plane is a flat surface, two-dimensional, that extends forever in every direction. And so along this line, these are my real numbers. And along this line, these are my imaginary numbers. But then anywhere else in any of these four quadrants, I have a combination of real and imaginary. So let's just say I pick a point right here. And I want to know what is the value of that point. Well, I'll start by looking at its real part. I have to shift over 3 to be under that point. So I start off by saying this is 3, and then I'm going to add to it its imaginary component. How far up do I have to go? I have to go up 2 i's. And in fact, that's actually the number that I call it. I say that this number is 3 plus 2i. And I can do that for any generic complex number here. I could just put a point somewhere on the plane and just say the first part is the real part. Where am I along the real axis? And then add to it the imaginary part, which would be times I, where I could say b represents a real number. Because take a look at this. If I were to remove the i's on this axis, it looks just like my real axis, doesn't it? It's just without i's. So this is 1, 2, 3. This is a -1, -2, -3. There's 0. So really, I could think about these coefficients as all being any real number. And so it's real plus real times imaginary in a way. And we often denote that with a lowercase z, although we don't have to. But it's this format right here is how we define our very last class of numbers. And I actually already gave it away just a little bit ago. It's what we call complex numbers. So for complex numbers, we use a capital C. We double curve on the left-hand side, and we define it to be equal to the set of numbers a plus bi. But we need to have some restrictions on that, such that, I'm going to go ahead and kind of get this out of the way here. A and b are real numbers, so we say they're elements of the reals, and I equals the square root of -1. And that is our last class of numbers. It's what we call the complex numbers. So notice how the complex numbers contain every number we've found up to this point. All of the real numbers are in here because I just set b equal to 0, and then I've got and then it's just a, it's all by itself. So I've got every real number is in the complex numbers. Also, every rational is in the complex numbers. Why? Because the real numbers contain all the rational numbers and all the irrational numbers as well. And thus, we'd have every integer because every integer is rational. And thus we have every natural, because every natural is an integer. Oh, and 0 is also included in here. Just let a and b be 0. So every number we've found so far is included in the complex numbers. And it gets even better. The reason why I said this is the last class is because there are no more numbers to be found. It's not like somewhere along the lines we're going to come along and say, well, I'm going to undo a different route and find a new type of super imaginary number. They actually just don't exist. And we know this because of something out there that's called the fundamental theorem of algebra. I'm going to save that for another day, probably a much later day, because it does involve some analysis, which we have not been dealing with yet. But it is the fundamental, as it says, and it basically does say that this is a closed set. And by closed set, we mean take any two complex numbers and perform any operation on them. Add them, subtract them, multiply them, divide them, raise them to any power, take them to any root. Those are the fundamental operations, and what do you get? You get a complex number every single time. And therefore, that's the highest set of numbers we can find. And there you have it, number classes. And remember, you watched it, you can't unwatch it.
It's obvious I'm wide and nerdy. Think I'm just too wide and nerdy. Think I'm just too wide and nerdy. I'm just too wide and nerdy. Look at me, I'm white and